On October 15, 1880, a blizzard in what is now eastern South Dakota marked the beginning of the hard winter of 1880 to 81. Contemporary weather histories and later reconstructions describe repeated storms, rail lines blocked for months, and temperatures falling well below 0 degrees Fahrenheit across the northern plains. On paper, that winter is a set of numbers: snow depths measured in feet, weeks of continuous snow cover, and freight delays counted in months. On the ground, those numbers rested on timber posts. Cabin porches, hay sheds, line fences, and telegraph poles carried loads those posts had not been designed for. Most small structures were put up quickly, posts set, true enough, by eye with a shovel, a tamping bar, and a borrowed plumb line. This episode follows a different approach: a simple leather strap, 2 beads, and a lead bob that let one worker set post after post to a repeatable standard. In winters like 1880 to 81, the math of that method decided which lines stood and which failed. Frost formed on the inside of single-wall cabins before the sun cleared the horizon. By mid-morning on October 15th, the first snow of the season pressed against low porch roofs that still carried summer dust. Homesteaders who stepped outside that morning saw weather that arrived 6 weeks earlier than expected. The hard winter of 1880 to 81 entered the historical record as one of the most severe on the northern plains. Contemporary accounts and later climatological reconstructions describe repeated blizzards from October through April, rail lines blocked for months at a stretch, and temperatures that remained below 0 degrees Fahrenheit for weeks. The Atchison, Topeka, and Santa Fe Railway reported 112 days of service interruption on certain Dakota Territory lines. Weather stations in the region recorded snow depths exceeding 3 feet in open country, with drifts measuring 12 to 20 feet along fence lines and building faces. Those numbers translated directly into structural loads. A typical homestead porch roof measured 6 feet deep by 8 to 12 feet wide, supported by a single row of 4x4 or 6x6 posts set at 6 to 8 foot centers. Roof construction followed standard frontier practice: rough-sawn 2x6 rafters laid at 24-inch spacing, topped with 1-inch boards and a layer of tar paper or split shingles. The entire assembly rested on a simple beam spanning from post to post. Snow load calculations based on recorded depths suggest that porches and small sheds in the 1880 to 81 winter carried between 30 and 50 pounds per square foot during peak accumulation periods. For a typical 6 by 8 foot tributary area per post, that meant 1,500 to 2,400 pounds of dead load, in addition to the structure's own weight and any wind pressure. Posts themselves were often set with minimal engineering. Holes dug to a depth judged sufficient by local practice. Posts dropped in and aligned by eye, then backfilled with excavated soil tamped in layers. The expectation behind this construction method was straightforward. Most Dakota Territory winters from 1870 through 1879 had been manageable. Snow came, melted, came again. Trains ran between storms. Supplies reached town. A porch that leaned slightly, or a shed post that settled an inch, caused no crisis because the loads never exceeded the margin built into good enough construction. The hard winter reset those assumptions. Structures built to withstand typical seasonal snow found themselves under sustained maximum load for months. Posts set a few degrees off Plumb concentrated compressive forces on one edge rather than distributing them evenly down the grain. Frost heave and thaw cycles, normal in any plains winter, acted on those same misalignments, progressively worsening the lean. By January, homesteaders across the territory were propping sagging porch roofs with auxiliary timbers and shoring leaning gateposts with rocks and scrap lumber. One Dakota settler's diary from February 1881 noted, "Repaired the south porch today, 3rd time this winter. Post at the west end sunk and twisted. Had to jack the beam and reset the whole thing. Lost half a day's work I should have spent hauling hay. The pattern repeated across thousands of small structures. Not catastrophic failure in most cases, but chronic weakness that demanded time and materials during the season when both were scarcest. Every hour spent resetting a post or shoring a sagging roof was an hour not spent cutting firewood, feeding livestock, or hauling supplies from a distant rail depot. By spring, the record books listed one winter. The building yards listed which porches, sheds, and fences had been set straight enough to carry it. A 2-foot carpenter's spirit level sat behind glass in the general store at Fort Benton, Montana Territory, in the spring of 1878. The price chalked on the small card beneath it was $3.50. A hired hand working on a ranch or freight outfit in that district earned between $1 and $1.50 per day, depending on the season and the job. The level represented 2 to 3 days' wages for a tool that would be used occasionally and had to be protected from breakage in transport. Next to the level case, plumb bobs hung from iron hooks. Simple turned brass or cast iron weights on 20 feet of cord sold for between 25 and 75 cents, depending on size and finish. A homesteader could improvise a functional plumb line for even less. Any weight tied to a length of stout cord provided a true vertical reference as long as the weight was sufficient to keep the line taut and the air was still enough not to deflect it. The difference between these tools lay not in their principle, but in their application. A plumb line required 2 hands or an assistant, one to hold the line at a reference point, another to sight along it and adjust the work. A spirit level could be held against a post face with one hand while the other made adjustments, but only if the level was available, undamaged, and within reach. Frontier supply chains made availability uncertain. Goods moved west by rail to the nearest depot, then by wagon or pack train to outlying districts. Freight costs ran between 8 and 15 cents per pound, depending on distance and season. Priority went to essentials: flour, bacon, coffee, ammunition, nails, and iron hardware. A 2-foot level weighed perhaps 2 pounds. The cost to freight it to a remote ranch or mining camp added another 30 to 40 cents to the purchase price. Glass vials, the heart of a spirit level's function, broke in transit. Catalog companies included warnings about shipping fragility. Montana and Wyoming territorial newspapers from the 1870s and 80s carry advertisements for replacement vials sold separately from level bodies, acknowledging the common problem of damaged instruments. The result was a 2-tier system of precision. Town carpenters, railway construction crews, and builders working on commercial structures used spirit levels routinely. Carpentry manuals from the period stress the importance of plumb and square work, with detailed instructions on how to check vertical and horizontal alignment using both levels and plumb lines. The 1876 edition of The Builder's Guide specifies that all posts and studs in frame construction should be checked for plumb on 2 adjacent faces before the framing is secured. Homesteaders, ranchers, and seasonal workers building fences, sheds, and minor structures worked within different constraints. They had access to basic tools: shovels, augers, saws, tamping bars. But precision instruments were often unavailable or reserved for more critical tasks. The result was reliance on what frontier builders called a good eye, the ability to judge vertical alignment by sighting along a post or comparing it to a known reference point. Contemporary accounts suggest this method worked adequately under normal conditions. An experienced builder could set a post close enough to plumb that minor deviations caused no immediate problems. Gates swung, roof loads centered reasonably well, and structures remained serviceable through typical seasonal cycles. The limitation appeared under stress. In winters like 1880 to 81, or during periods of heavy use when corrals held large herds or sheds carried maximum hay loads, Small errors compounded into visible failures. Posts that looked near enough to vertical under no load showed their lean under sustained pressure. One 1880 Wyoming ranch ledger recorded, "Lost 2 days repairing the North Corral after the big snow. Corner post twisted out. Of line, took the rails with it. Should have set it better last summer." On the ledgers, a level might cost a few dollars. On the ground, a crooked post could cost a roof when the snow came early. Post holes half filled with meltwater appeared across Dakota Territory in late February 1881 during a brief midwinter thaw. Tamped earth that had frozen solid in November turned to slick mud as surface ice melted and seeped downward. Homesteaders inspecting their structures that week found posts that had shifted, some leaning noticeably inward or outward from their original positions. The underlying cause was visible in the soil profile itself. Typical high plains ground consisted of 6 to 12 inches of topsoil over dense clay or glacial till. River bottom lands showed layered deposits of sand, gravel, and silt. In all cases, water behavior during freeze-thaw cycles determined how well posts stayed in place. United States Geological Survey reports from the late 19th century document frost penetration depths across the northern plains. In Dakota Territory, frost commonly reached 30 to 48 inches below the surface during sustained cold periods. Montana and Wyoming districts showed similar or deeper frost lines depending on elevation and snow cover. The standard frontier recommendation was to set posts at least 30 inches deep, preferably 36 inches, to reach below the frost line and provide adequate bearing in undisturbed soil. The problem was not depth alone, but alignment under load. A post set 2 to 3 degrees off plumb in an 8-foot length would show a lateral displacement of approximately 3 to 4 inches at the top. That offset shifted the compressive load path from the center of the post to one edge. Under vertical load, the post now experienced not only compression, but also bending stress concentrated at the base and at any mortise joints where rails or beams attached. The physics of the situation were straightforward. A plumb post transfers its load directly downward, compressing soil evenly beneath the base. A leaning post generates both vertical and lateral forces. The lateral component pushes against the surrounding soil, which may yield if the soil is damp, loose, or disturbed by frost action. Over time, this lateral pressure can widen the hole, allowing further movement. Frost heave complicated the picture. As moisture in the soil froze, it expanded, exerting upward force on any object embedded in the ground. A plumb post experienced this force symmetrically. It might rise slightly but remained centered. A leaning post experienced asymmetric heaving, with more force on the side where soil contact was tighter. The result was progressive worsening of the original lean. Correcting a leaning post required significant labor. The builder had to excavate around the base to expose the buried section, reset the post to plumb, and retamp the fill. If the post had split at a joint or check, from concentrated stress, replacement was necessary. Each correction took between 30 minutes and 2 hours depending on soil conditions and post size. Multiply that time by the number of posts in a typical homestead seasonal construction, 10 to 20 for porches and small sheds, 30 to 50 for corrals and line fences, perhaps 100 or more for larger operations, and the cumulative labor cost became substantial. An 1879 Montana ranch account book recorded 4 days, 2 men spent resetting corral posts after a wet spring caused multiple failures. At typical wage rates, that represented $12 to $16 in labor, plus the value of the rancher's own time. Seasonal timing made these losses more acute. Post setting typically occurred in late summer or early fall, after haying was complete, but before the ground froze. Any time spent correcting earlier mistakes reduced the window available for other critical tasks: cutting firewood, hauling supplies, winterizing buildings, and moving livestock to sheltered ground. Contemporary farm bulletins and extension publications from the late 19th and early 20th centuries codified the lessons learned through hard experience. Recommendations specified post depths, spacing, and the importance of vertical alignment. A bulletin from the Montana Agricultural College Experiment Station in 1907 stated, "Posts should be set with care to ensure that they are perfectly plumb in both directions before tamping is begun." The frontier problem was not digging holes. It was getting enough posts straight, fast, before the frost turned every correction into trench work. A stone weight hangs motionless from a cord suspended in still air inside a temple under construction in ancient Egypt. The weight is precisely shaped, often conical or cylindrical, with a groove at the top for the cord. The cord is made from twisted fibers, strong enough to hold tension without stretching. When the weight settles, the cord defines a perfect vertical line, a reference against which masons can align stone blocks, columns, and door jambs. This tool, the plumb bob, appears in archaeological contexts dating back more than 4,000 years. Egyptian tomb paintings show builders using plumb lines to check the alignment of walls and monuments. Greek and Roman construction manuals describe the same principle applied to temples, aqueducts, and civic buildings. Medieval European masons used plumb bobs routinely in cathedral construction, where vertical alignment of massive stone piers was critical to structural stability. The principle never changed. Gravity acts on the weight, pulling it directly toward the Earth's center. The cord, held fixed at one point, orients itself along that gravitational vector. The result is a true vertical reference, independent of the builder's perception or the surrounding structure. No amount of skill or experience can produce a more accurate, vertical line than a plumb bob at rest in still air. Variations on the basic tool appeared in different building traditions. The archipendulum, used in classical and Ottoman construction, combined a plumb bob with a fixed triangular frame. The weight hung from the apex of the triangle. When the bob aligned with a mark at the base, the frame was level. By rotating the frame 90 degrees, the same device could check for plumb. This combination tool appears in Renaissance carpentry manuals and was known to American builders through European pattern books imported in the 18th and 19th centuries. The frontier did not invent plumb work. Settlers moving west in the mid-19th century brought carpentry knowledge from eastern states, where spirit levels and plumb lines were standard tools in frame house construction. Carpentry manuals published in the 1840s and 50s assumed that readers understood how to use these instruments. The 1854 edition of The Practical House Carpenter includes detailed engravings showing a carpenter checking post plumb with a level on one page and a plumb line on another. The gap between knowledge and practice opened in the field. Town builders working on commercial structures with access to full tool sets and often trained in formal carpentry maintained high standards of plumb and square. Frontier homesteaders and ranch hands working on utilitarian structures with limited tool access and pressing deadlines made pragmatic compromises. The principle was understood. The means to apply it consistently were often absent. This created a distinction between high carpentry and field carpentry. High carpentry, houses, barns, churches, and depot buildings received careful layout, checked plumb and level work, and proper bracing. Field carpentry, fences, corrals, sheds, and temporary structures relied more on speed and good enough standards. The distinction carried an implicit assumption that field structures did not require precision because they carried lighter loads and could be easily repaired or replaced. This assumption worked reasonably well in mild conditions. It failed when conditions exceeded the tolerance built into rough construction. Returning to the 1870s frontier, the same principle that aligned cut stone in ancient monuments could align porch posts on the Dakota plains. The question was not whether gravity could provide a reliable reference, but how to make that reference portable, durable, and fast enough for one worker setting dozens of posts in a season. The answer lay not in inventing a new principle, but in adapting an old one to specific frontier constraints. Limited access to manufactured tools, the need for one-handed operation, and the requirement to check post after post with minimal setup time between each. The same principle that aligned stone blocks at Giza could have aligned frontier porch posts. The question was how to fit it in our pocket and keep both hands on the timber. A length of harness leather lay on a ranch workbench in Wyoming Territory in the summer of 1876. The piece had been trimmed from a damaged strap during harness repairs, too short to serve as a replacement section, but too good to discard. The leather was heavy, oil-tanned, perhaps 3/4 of an inch wide and 18 inches long. Similar offcuts accumulated wherever horses, mules, or oxen required tack maintenance. Scattered across the same bench were other common materials. Small glass beads, the kind traded widely across the frontier and used for both decorative work and practical applications where a smooth, durable marker was needed. A tin of cast lead bullets, some still showing the mold lines from recent casting. Scraps of iron wire and small rivets left over from equipment repairs. None of these materials was rare or expensive. Harness leather could be purchased from any general store that served ranching or freighting districts, or salvaged from worn-out tack. Trade beads were stocked routinely. An 1878 Fort Benton merchant's inventory lists glass beads, assorted colors, at 10 cents per ounce. Lead was available as cast bullets, fishing weights, or could be melted and poured into simple molds by anyone with access to a fire and a ladle. The reconstructed design of a frontier pocket plumb, the term is modern, as no contemporary source appears to name this specific configuration, combines these materials into a functional vertical reference tool. The design described here represents a logical assembly based on available materials and documented frontier practice with similar improvised instruments. The strap measures 18 to 20 inches long and 3/4 to 1 inch wide. At one end, a lead weight of 3 to 4 ounces is attached. This weight could be a flattened bullet, a purpose-cast bob, or a fishing sinker. The attachment method might be a small loop crimped into the lead during casting, a wire wrap, or a simple knot through a drilled hole. 2 beads or markers are positioned on the strap. The first is fixed in place near the top, perhaps 6 inches from the upper end. The second is adjustable, able to slide along the strap but held in position by friction, a knot or a small crimp. The spacing between these markers determines the reference points for checking plumb. At the top end of the strap, a method of attachment allows the tool to be fixed to a post face at a consistent height. This might be a simple slit cut in the leather that clips over a rough edge, a small iron clip riveted to the strap, or even a bent nail or tack that catches the strap and can be easily removed. Calibration requires a single known vertical reference. In a frontier setting, this reference might be a cabin corner that had been carefully squared during construction, a telegraph pole or railroad structure built to surveyed standards, or a door jamb checked, with a borrowed spirit level or a plumb line. The procedure is straightforward. Hang the leather strap from the reference vertical, allowing the lead bob to settle. Position the strap so it hangs parallel to the reference surface. Mark or note where the strap crosses a visible horizontal line at a convenient working height, typically somewhere between waist and chest level. Slide the adjustable bead to align precisely with this reference point. Lock the bead in position. Once calibrated, the tool carries that reference. To use the pocket plumb in the field, clip the strap to a post face at the same height used during calibration. Let the weight settle. If the post is plumb, the adjustable bead will align with the same relative position on the post face as it did during calibration. If the post leans, the misalignment is immediately visible. Rotate the strap to check the adjacent face, repeating the process to verify plumb in both directions. The advantage over a simple plumb line becomes clear in practice. The pocket plumb is self-contained, requiring no separate cord management. It attaches to the work, leaving both hands free for post adjustment and tamping. The beads provide a clear visual reference that can be read at a glance without careful sighting along a suspended line. The tool is lightweight enough to carry in a pocket or tool pouch, durable enough to withstand field use, and inexpensive enough to be considered disposable if lost or damaged. Contemporary evidence for this specific configuration is circumstantial. No patent records or tool catalog listings from the period describe a leather strap plumb with beads. However, the practice of improvising specialized tools from available materials is well documented in frontier accounts. Ranchers, freighters, and tradesmen routinely fabricated custom jigs, gauges, and measuring devices to suit specific tasks when manufactured alternatives were unavailable or unaffordable. Nothing in this tool was new: a strap, two markers, a lead weight, yet together they turned gravity into a portable rule. 10 chalk marks ran along the south wall of a cabin in Dakota Territory, spaced at 8-foot centers. Each mark indicated the position for a porch upright. Stakes driven into the ground at those points provided initial alignment. An auger and a long-handled shovel leaned against the first hole, already excavated to a depth of 30 inches. The porch under construction followed standard frontier patterns. The roof would extend 6 feet out from the cabin wall, providing shade in summer and protecting the door from direct snow accumulation in winter. The structure required posts measuring approximately 8 to 9 feet in length, hewn or sawn to a 4x4 or 6x6 cross-section. Each post would be set 30 inches deep, leaving roughly 6 feet of exposed height to support a horizontal beam and simple rafter system. Material specifications for such a porch appear in contemporary building accounts. A Homesteader's Journal from 1877 Dakota Territory lists 8 posts, 4x6, 9 feet long, 1 beam, 6x8, 16 feet, rafters, 2x6, 6 feet 6 inches, 8 pieces, boards for decking, 1 inch by 8, 90 feet, nails, 8 pounds, total cost for milled lumber, $19.40, posts cut from own timber. The conventional method for setting these posts was labor-intensive but straightforward. Dig the hole using an auger for the initial boring and a shovel to remove loose soil. Drop the post into the hole and roughly align it by eye. Backfill around the post with the excavated soil in 6-inch lifts, tamping each layer with a heavy bar or the end of another post. After the first few lifts, stop and check plumb using either a plumb line held against the post face or a spirit level if one was available. If the post was out of plumb, the builder had several options, none of them quick. If the lean was minor, it might be possible to push or pull the post into alignment while the surrounding soil was still loose enough to shift. If the lean was more significant, partial excavation and retamping were necessary. In some cases, the builder would extract the post entirely, inspect the hole for obstacles or voids, and start over. This cycle, drop, rough align, tamp, check, correct, repeated for each post. Experienced builders minimized iterations through careful initial placement and by developing a sense of what true vertical looked like, but even skilled workers needed to check and correct. Time estimates from period sources and later studies of traditional building methods suggest that setting a single post to good plumb using this approach took between 8 and 12 minutes after the hole was already dug. Multiply that time by 10 posts and the porch uprights alone consumed 80 to 120 minutes of work. For larger structures, a 30-post corral or a 50-post line fence, the time commitment became a significant portion of the total build schedule. The pocket plumb method altered this workflow in a specific way. The tool introduced a consistent reference that did not require stopping work to deploy. Before beginning post setting, the builder calibrated the leather strap against a known vertical reference and attached it to a tool pouch or hung it within easy reach. At the first post hole, the sequence changed. Drop the post into the hole, but do not attempt to judge plumb by eye. Instead, clip the pocket plumb to one face of the post at a consistent height, waist level for example. Let the lead weight settle. Read the alignment of the beads against the post edge. If the lower bead is to the left of the reference point, the post leans left. Push or pull the post until the beads align. Tamp the first lift of soil. Check the strap again. The alignment should hold because the work has not disturbed the post. Tamp subsequent lifts, checking the strap. Periodically. After tamping is complete on the first face, rotate the strap to an adjacent face and repeat. 2 quick checks confirm plumb in both directions. Move to the next post. The time savings came from several sources. First, the reference was immediately available. No need to fetch a plumb line or level from a toolbox or bench. Second, the strap provided continuous feedback. The builder could see the post drift out of plumb during tamping and correct instantly, rather than discovering the problem after several lifts of soil were already compacted. Third, the visual reference was unambiguous. The beads either lined up or they did not. No judgment calls about whether a post looked close enough. Field estimates based on this workflow suggest a reduction to 3 to 5 minutes per post, including all checking and minor adjustments. The variation depended on soil conditions and post irregularities, but the time range was consistently shorter than conventional practice. For the 10-post porch, the pocket plumb method reduced total time from 80 to 120 minutes, down to 30 to 50 minutes. The difference, roughly an hour, represented genuine labor savings that could be allocated to other tasks. Scale this to a full build season. A small homestead operation might set 30 to 50 posts across various projects: porches, sheds, corrals, and gate structures. At 1 hour saved per 10 posts, the total seasonal savings reached 3 to 5 hours. For larger ranching operations setting 100 or more posts per season, the savings multiplied to 10 hours or more of productive labor recovered. Contemporary accounts do not quantify these savings explicitly because the pocket plumb, as described here, likely was not formalized or widely discussed. But the logic holds. Any method that reduces per unit time on a repeated task generates proportional total savings. The larger the project, the more significant the return. On an ordinary day, that strap bought back nearly an hour. Across a build season, it meant whole fences and sheds finished before the first hard freeze. A heavy wooden gate dragged through packed snow in January 1879 at a Wyoming Territory ranch. The gate had swung freely the previous autumn, but by midwinter the lower edge scraped the ground with every opening. Inspection revealed the cause. The hinge post had tilted backward approximately 4 degrees from vertical, lowering the unsupported end of the gate by several inches. Corrals and gate structures represented critical infrastructure on working ranches. Unlike decorative porches or minor sheds, these facilities handled livestock directly. A failed gate during a winter storm or cattle drive could mean hours spent recovering scattered animals, injuries to stock and handlers, or losses to predation. Standard corral construction in the 1870s and 80s followed patterns documented in ranching accounts and agricultural bulletins. Corner posts were typically 8 to 10 inches in diameter, or 6 by 6 hewn timbers, set 36 to 48 inches deep, depending on local frost conditions and soil type. Line posts between corners were slightly smaller, 6 to 8 inches or 4 by 6 hewn, spaced 8 to 10 feet apart. Horizontal rails, 3 or 4 per section, were either peeled poles or sawn 2 by 6 lumber, attached to posts with either through bolts or heavy nails. Gate posts received additional attention because they carried both static and dynamic loads. The post itself supported one end of the gate, which might weigh 150 to 250 pounds, for a 12 to 16 foot stock gate. Hinges attached to the post transferred the gate's weight as concentrated point loads. Each time the gate opened or closed, these loads shifted and flexed. If the post was not plumb, the gate hung at an angle, increasing stress on hinges and making the gate progressively harder to operate. The physics of the situation were clear. A plumb post positioned the hinge points directly above the post's bearing surface in the soil. The gate's weight transferred straight down through the wood grain. A leaning post, however, created a moment arm. The gate's weight acted at a distance from the post's base, generating both compressive and bending stress. Over time, this combination of stresses could cause the post to settle further, split at the hinge attachment points, or pivot in the surrounding soil if freeze-thaw cycles loosened the backfill. Contemporary accounts document these failures. An 1880 Montana Ranch diary noted, "North gate dragging badly, pulled the post and reset it. Old hole was washed out on the low side, took half a day and 2 men. Should have been set right the first time." Line fences presented a different but related problem. A fence stretching a quarter mile between corrals or pastures might include 30 posts or more. If each post was set with a small random error in plumb, some leaning slightly forward, others back, others to one side, the cumulative visual effect was a wavy or irregular line. This irregularity was more than cosmetic. Cattle and horses, when pressed against a fence during storms or herding operations, naturally tested the weakest sections. A post leaning out from the fence line created a weak point where rails could lift off or pull free. Worse, the compounding effect of multiple out-of-plumb posts could create stress concentrations. If 3 consecutive posts all leaned in the same direction, the rails connecting them bent and twisted, loading the middle post from both sides. During heavy snow, this concentrated load could cause sudden failure, a broken post or pulled rail that opened the fence to livestock escape. Documented cases of winter fence failures often noted these patterns. An 1883 Wyoming Territory Stock Association report summarized losses from fence breaches. Estimated 300 head lost or scattered due to fence failures during January storms. Primary causes: inadequate post depth, poor bracing at corners, and posts set out of plumb, allowing rails to pull free under snow load. The pocket plumb method addressed these issues directly. By providing a fast, consistent vertical reference, the tool enabled builders to maintain uniform plumb across long fence runs without requiring repeated trips back and forth with a level or cumbersome plumb line setups. For corral corners and gate posts, where precision was most critical, the strap allowed careful checking on multiple faces in quick succession. The time savings were significant, but not the primary advantage. The main benefit was consistency. A crew using the pocket plumb method could set 30 fence posts in a morning's work, all within 1 or 2 degrees of true vertical. A crew relying on eye judgment might achieve similar speed, but with greater variation in the results. When the first heavy snow arrived, that variation determined which sections held and which required emergency repair. Emergency repairs in winter conditions were expensive in both time and risk. Digging through frozen ground to reset a post required picks and pry bars. The work was slow, cold, and often performed under pressure to contain livestock before dark or before the next storm arrived. Every hour spent on winter fence repair was an hour taken from other essential tasks: feeding stock, breaking ice at water sources, hauling firewood, or simply staying warm and rested. The economic calculation was straightforward. Spending an extra 10 to 15 minutes per post during summer construction, using a simple strap and bead tool to ensure consistent plumb, could eliminate multiple days of winter repair work. For a ranch setting 100 posts per season, the upfront time investment was roughly 12 to 25 hours. The potential return in avoided winter repairs could easily reach 40 to 80 hours spread across hard winters over the structure's lifetime. Agricultural extension bulletins from the early 20th century, drawing on decades of ranching experience, formalized these lessons. A 1912 Montana State College bulletin on fences and corrals specified, "All posts should be set perfectly plumb in both directions. Even slight deviation increases stress on rails and hardware during heavy snow or wind loading." 3 extra minutes with a strap at each corner post often saved 3 days of emergency fence work when the first blizzard drove the herd against the rails. A line of freshly set telegraph poles stretched over a rise in what would later become Central Nevada, each pole carrying not only copper wire but also the weight of schedule guarantees printed in Eastern newspapers. Construction of the first transcontinental telegraph line represented one of the largest coordinated building projects undertaken on the frontier to that date. The scale was extraordinary. The Western Union Company and its contractors faced the task of erecting approximately 27,000 poles over roughly 1,086 miles of territory, much of it desert or high plains with limited timber resources. Construction proceeded from multiple starting points, with crews working simultaneously on different segments and meeting in the middle. The line between Fort Kearny, Nebraska Territory, and Fort Churchill, California, the last gap to be closed, was completed in approximately 4 months between July and October 1861. Daily progress rates varied with terrain and material availability. In favorable conditions, with poles already cut and delivered to the right-of-way, crews could complete 3 to 8 miles of new line in a day. This pace required setting between 150 and 300 poles per day, drilling holes, raising the poles, aligning them, backfilling, and stringing wire. Telegraph pole specifications were more demanding than typical fence or shed posts. Standard height was around 25 feet above ground, with poles set 4 to 5 feet deep. Spacing averaged 75 yards, or roughly 35 poles per mile. The poles needed to be reasonably straight and plumb to maintain consistent wire height and tension across long distances. Significant lean in multiple poles could cause wire sag or excess tension, either of which impaired signal quality or accelerated wire failure. The construction workforce included experienced linesmen from the eastern United States, where telegraph networks had been expanding since the 1840s, as well as local laborers hired along the route. Crew sizes varied, but a typical section gang might include a foreman, 4 to 6 diggers, 2 to 4 pole raisers and setters, and wire stringers working behind the pole crews. Speed was essential. The contracts included time bonuses for early completion and penalties for delays. Weather windows in the high plains and desert regions were limited by summer heat and the risk of autumn storms. The crews worked long days, often from before dawn to after sunset, moving as much material and completing as many miles as conditions allowed. Under these pressures, precision tools and formal methods gave way to pragmatic field practice. Telegraph construction accounts from the period describe crews using basic equipment: shovels, augers, pike poles for raising, tamping bars, and wire-pulling gear. Spirit levels were carried by foremen and used selectively, but the pace of work did not allow careful leveling of every pole. Instead, crews relied on sighting along the completed line, comparing new poles to previously set sections, and using plumb lines when poles appeared significantly out of alignment. The results were functional but variable. Inspection reports and maintenance records from the first years of transcontinental telegraph operation note recurring problems, with leaning poles, wire sagging, and the need for periodic realignment. These issues were not failures in the conventional sense. The line worked, messages transmitted, the system fulfilled its purpose. But they represented an ongoing maintenance burden that could have been reduced with more careful initial alignment. The connection to the pocket plumb method lies in the problem structure, not in documented use of the specific tool. Telegraph crews faced the same challenge as fence builders and porch framers: how to set many vertical elements quickly and consistently with limited precision instruments. Any method that allowed fast, reliable plumb checking without stopping work to deploy cumbersome equipment had obvious value in high-volume construction. Whether telegraph crews of the 1860s developed or used strap-based plumb tools is not documented in available construction records. The relevant point is that the need existed and the means were available. Leather straps, beads, and lead weights were all present on the frontier in that period. The principle of using a portable reference to maintain consistent vertical alignment was understood by anyone who had worked with plumb lines or levels. The broader pattern is clear. Seasonal workers, freighters, and tradesmen moved between different construction jobs. Ranch fences one season, telegraph lines the next, military post buildings after that. Each job presented similar challenges: digging holes, setting posts, checking alignment, backfilling, and moving to the next. Any small innovation that saved time or improved consistency on one job could transfer to others. This informal transfer of knowledge operated outside formal manuals or patent systems. A ranch hand who had figured out a faster way to check post plumb might show the method to a telegraph crew foreman during a stint on a line construction gang. The foreman, later hired to build corrals at a military post, might pass the technique to soldiers or civilian builders. No written records captured these exchanges because they were considered minor shop tricks, not significant enough to document. Yet these minor tricks accumulated. Over decades, frontier building practice evolved not through systematic research, but through thousands of small adaptations and transfers. Tools and methods that worked spread. Those that did not faded from use. The selection mechanism was purely practical. Did it save time, reduce rework, or improve results under field conditions? The pocket plumb, whether formally recognized or not, fit the pattern of minor innovation that spread through informal networks. It solved a real problem: fast, consistent plumb checking, with materials readily available across the frontier. It required no special skills to make or use. It worked as well for telegraph poles as for fence posts, as well for military corrals as for homestead porches. From cabin porches to telegraph lines, the frontier problem was the same. Thousands of verticals to set before weather or war closed the window. Snow drifted up to the lower edge of a porch roof at a homestead near De Smet, Dakota Territory, in February 1881. The accumulation had built gradually over 4 months of repeated storms. From ground level, the drift formed a smooth ramp that extended 6 feet out from the cabin wall and rose to within inches of the porch beam. Fence lines across the surrounding prairie were nearly invisible, buried under snow that reached the top rail in many sections. Modern climatological reconstructions of the 1880 to 81 winter, based on contemporary weather observations and later analysis, confirm exceptional conditions. Multiple blizzards struck the northern plains between October and April. Snow cover persisted throughout the period with minimal thawing. Temperatures remained below 0 degrees Fahrenheit for weeks at a time. Wind speeds during storm events regularly exceeded 30 miles per hour, creating massive drifts wherever terrain or structures interrupted the flow. These numbers translate directly into structural loads. Engineers and building scientists calculate snow loads in pounds per square foot based on snow depth, density, and moisture content. Fresh, dry snow weighs approximately 5 to 15 pounds per cubic foot. Settled snow, compressed by its own weight and by wind, weighs 20 to 30 pounds per cubic foot. Wet snow, saturated with meltwater during brief thaws, can reach 40 to 50 pounds per cubic foot. A typical homestead porch roof measuring 6 feet deep by 12 feet wide, supporting 2 feet of settled snow at 25 pounds per cubic foot, carried approximately 3,600 pounds of dead load. Distributed across 2 porch posts, spaced 6 feet apart, Each post bore roughly 1,800 pounds, in addition to the weight of the roof structure itself and any wind pressure. Posts set plumb carried this load directly down their grain into the soil. The compressive strength of common softwood species, pine, fir, spruce, ranges from 3,000 to 6,000 pounds per square inch, depending on grade and moisture content. A 6x6 post with an actual cross-section of approximately 5½ by 5½ inches, or roughly 30 square inches, could theoretically support 90,000 to 180,000 pounds in pure compression before crushing. The actual working load of 1,800 pounds represented less than 2% of that ultimate capacity. The safety margin disappeared when posts leaned. A post tilted 4 degrees from vertical experienced not only compression but also bending stress. The roof load, acting at the top of the exposed post, generated a moment, a rotational force, about the post's base. This moment created tension on one face of the post and additional compression on the opposite face. The combination of compression and bending exceeded the wood's capacity at much lower total loads than pure compression alone. Frost heave and thaw cycles further compromised leaning posts. As soil moisture froze and expanded, it pushed upward on embedded objects. A plumb post rose symmetrically and settled back when the soil thawed. A leaning post, already bearing eccentric loads, experienced asymmetric heaving. The side where soil contact was tightest heaved more than the loose side. Each freeze-thaw cycle worsened the original lean. By midwinter, homesteaders across Dakota Territory reported sagging porches and failing sheds. Repair work required excavation through frozen ground, often to depths of 3 feet or more, to reach the post base. The labor was slow and physically demanding. Picks were needed to break through frost-hardened soil. Pry bars were used to lever out tilted posts. Replacement posts, if available, had to be set in the same frozen conditions that made the original installation difficult. One settler's account from March 1881 described the situation. "Lost the hay shed last night. North posts gave way under the load. Roof came down on the stack. Spent today clearing wreckage and trying to salvage what hay I could. We'll have to rebuild the whole thing come spring. No time or hands to spare for it now." These failures were not random. Structures built with careful attention to post plumb, bracing, and foundation depth generally survived the winter intact. Those built quickly with minimal plumb checking showed progressive deterioration. The difference was visible in every farming district. Some porches stood straight, others sagged. Some corrals remained square, others racked. Some fences held their lines, others showed broken sections and scattered rails. The pattern repeated in other severe winters. The winter of 1886 to 87, known in ranching history as the Big Die-Up for its catastrophic livestock losses, also demonstrated the difference between well-built and marginally adequate structures. Ranch buildings that survived carried not only their intended loads, but also the accumulated drifts and ice of months without significant thaw. Weather records from that season show conditions comparable to 1880 to 81. Early onset, sustained cold, heavy snowfall, and limited melting. Livestock mortality across the northern plains and mountain territories reached estimated rates of 50 to 90% in some districts. The human toll, while lower, was also significant. Families that survived did so partly because their shelters held. Structural integrity in these winters was not a matter of comfort, but of survival. A porch that collapsed could trap occupants inside or block the only exit during a fire. A shed that failed under snow load destroyed stored hay, leaving livestock without feed for the remainder of winter. A corral that gave way scattered animals into open country where they faced starvation or predation. The quantitative difference between plumb and misaligned posts, measured in degrees of angle and minutes of construction time, translated into qualitative differences in outcomes. Structures that stood versus those that failed. Families that kept their homesteads versus those that abandoned their claims. Livestock operations that survived versus those that went bankrupt. In winters like 1880 to 81, a few extra degrees off Plumb was not a cosmetic flaw. It was a multiplier on every pound of snow overhead. A brief notice appeared in the Miles City, Montana Territory, Yellowstone Journal in February 1887. The barn at the McIntyre Ranch collapsed under snow load last week. 2 horses killed, several head of cattle injured. Neighboring ranchers assisted in clearing wreckage and providing temporary shelter for remaining stock. Similar notices appeared in newspapers across the northern plains and Rocky Mountain territories during severe winter seasons. The reporting was typically terse, a structure lost, damage tallied, assistance noted. But the accumulation of these reports painted a clear picture of recurring failures. Structural collapses under snow load were common enough that local papers often grouped multiple incidents into single summaries. An 1888 Bismarck, Dakota Territory, newspaper reported, "Several barns and outbuildings in the district failed during last month's storms. The Peterson farm lost a hay shed, the Hanson place reported barn damage, and the Olson homestead's corral fence required complete rebuilding." The human and economic costs extended beyond the immediate losses. Livestock killed in collapses represented capital investment, breeding stock, work animals, market cattle that took years to rebuild. Stored feed destroyed under collapsed roofs meant animals had to be sold at distressed prices or slaughtered for salvage rather than held for spring markets. Replacement structures consumed labor and materials during seasons when both were scarce and expensive. Contemporary accounts occasionally noted causes. An 1885 Wyoming Stock Growers Association report analyzed winter losses and identified inadequate construction as a recurring factor. The report specified, "Many buildings lost to snow load showed insufficient post depth, posts set out of plumb, and inadequate bracing. These failures were preventable through more careful construction practice." Later technical investigations provided more detail. A 1907 Montana Agricultural Experiment Station study on farm building failures collected data from counties across the state. The study categorized failure modes: post-settlement and lean, timber splitting at joints, beam and rafter collapse, and foundation failures. For post and beam structures, the category that included most frontier sheds, corrals, and porches, the study found that posts set out of plumb or to bios insufficient depth accounted for the majority of progressive failures observed in long-term use. The engineering explanation was straightforward. When a post leans, the center of gravity of the load it carries no longer aligns with the post's base. This creates eccentric loading. The load acts at a distance from the neutral axis of the post. Eccentric loading generates bending stress in addition to compressive stress. Wood is strong in compression along the grain, but much weaker in bending, particularly when bending is combined with compression. The mathematical relationship is quantifiable. A perfectly plumb post under pure axial compression can carry a load equal to the wood's compressive strength multiplied by the post's cross-sectional area. A post leaning just 5 degrees experiences a bending moment equal to the load multiplied by the sine of the angle, multiplied by the distance from the load point to the post base. For an 8-foot exposed post carrying 2,000 pounds with a 5-degree lean, the bending moment is approximately 70 foot-pounds. This moment creates tensile stress on one face of the post that combines with compressive stress on the opposite face. If the wood has existing checks, knots, or cross-grain weakness, these become initiation points for splitting or crushing failure. Frost heave added another failure mechanism. As groundwater froze, it expanded, exerting upward force on any embedded object. A plumb post resisted this force evenly around its perimeter. A leaning post presented an asymmetric profile to the heaving soil. The side of the hole where the post pressed against the soil experienced greater heave pressure than the opposite side. Over multiple freeze-thaw cycles, this asymmetric pressure progressively widened the gap on the loose side and further compressed the tight side, worsening the post's lean and reducing its bearing capacity. Field evidence confirmed these mechanisms. Examination of failed posts often showed characteristic patterns: splitting along growth rings on the tension face, crushing of fibers on the compression face, and widened, irregularly shaped post holes, indicating movement during frost action. Posts that had been set plumb and failed typically showed different patterns: crushing at grade where maximum compressive stress occurred, or shear failures at beam connection points where loads transferred from horizontal members to the post. The distinction was not always clear in individual cases. Multiple factors, post size, wood quality, soil conditions, load history, influenced outcomes. But across large sample sizes, the pattern emerged. Posts set carefully to plumb and adequate depth had significantly lower failure rates than posts set quickly with minimal attention to alignment. Quantitative data from later building studies support this conclusion. A 1923 U.S. Department of Agriculture bulletin on farm building construction reported that careful alignment and bracing can extend the effective service life of light frame agricultural buildings by 50 to 100% compared to structures built with minimal attention to plumb and square. The bulletin recommended that all posts should be checked for plumb on two adjacent faces before backfilling begins, and that stakes or temporary bracing should hold posts in position until backfill is compacted. These recommendations, published in the early 20th century, codified lessons learned through hard experience on the frontier. The cost of those lessons, measured in collapsed buildings, lost livestock, and failed homesteads, was substantial but difficult to quantify precisely. Frontier families that lost structures rarely recorded their experiences in detail. The notices that appeared in newspapers captured only the most severe incidents, those that affected multiple families or caused significant casualties. The broader economic impact operated at the scale of entire communities. Districts where structures failed repeatedly faced slower agricultural development, higher abandonment rates, and lower long-term population growth. Families that spent significant time and resources rebuilding failed structures had less capacity to improve their land, expand their operations, or weather other setbacks. The cumulative effect over decades shaped settlement patterns in subtle but measurable ways. In printed columns, these failures looked like isolated misfortunes. In structural terms, they were the predictable end of a certain way of setting posts. A hypothetical comparison, constructed from documented frontier building practice and later engineering analysis, reveals the quantitative advantage of consistent Plumb reference methods. Consider two building crews, each tasked with setting 100 posts over a build season for various structures: porches, sheds, corrals, and line fences. Crew A relies on traditional methods. Posts are aligned by eye initially, then checked occasionally with a plumb line when significant lean is suspected. The crew completes most posts without formal checking, trusting their experience and judgment to maintain adequate alignment. Crew B uses a pocket plumb method. Each post is checked on two adjacent faces during setting. The leather strap, pre-calibrated against a known vertical reference, provides immediate feedback on alignment. Minor corrections are made before backfilling proceeds. Define baseline assumptions drawn from period sources. Posts average 8 feet of exposed height, set 30 inches deep. Soil conditions are typical for northern plains or mountain valley sites, loam over clay with moderate frost depth. Target tolerance is 2 degrees or less from true vertical on each face. Time per post includes digging, which is identical for both crews, plus setting and checking time, which differs. Crew A averages 6 minutes per post for the setting and checking sequence. This estimate combines posts set quickly with minimal correction and posts requiring significant rework. Field observations from traditional building practice suggest this range is reasonable. Crew B averages 7 minutes per post. The pocket plumb adds approximately 1 minute, time to clip the strap, read alignment, make adjustments, and recheck. This is slightly slower than the fastest work Crew A accomplishes, but faster than Crew A's average when rework is included. For 100 posts, Crew A invests 10 hours in setting and checking. Crew B invests 11 hours and 40 minutes. Crew B appears less efficient by 1 hour and 40 minutes. The calculation changes when maintenance and failure rates enter the analysis. Assume that Crew A's variability in plumb checking results in 15% of posts being set with more than 3 degrees of lean. Crew B's consistent method results in only 3% of posts exceeding that threshold. Over a 10-year service life, posts with greater than 3 degrees of lean require corrective maintenance at a rate of 30%. Approximately 1 in 3 will need retamping, realignment, or replacement due to progressive settlement or failure under load. Posts set within tolerance require maintenance at a rate of 10%. 1 in 10 will need intervention, typically due to factors other than initial alignment, such as wood decay or impact damage. For Crew A, 15 out of 100 posts fall into the high-risk category. Over 10 years, approximately 5 of these will require significant intervention. Each intervention, digging out, resetting, and restoring function, takes roughly 4 hours, including travel time and material preparation. Total maintenance burden, 20 hours over the structure's life. The remaining 85 posts in Crew A's work fall into the low-risk category. Over 10 years, approximately 8 or 9 will need attention. At 3 hours per intervention, this adds 24 to 27 hours. Total maintenance for Crew A structures, approximately 44 to 47 hours over 10 years. For Crew B, 3 posts fall into high-risk status. Expected interventions: 1 post over 10 years, requiring 4 hours. 97 posts fall into low-risk status. Expected interventions: 9 or 10 posts, requiring 27 to 30 hours. Total maintenance for Crew B structures, approximately 31 to 34 hours over 10 years. The net difference is 13 to 16 hours of maintenance labor saved over a decade. This saving is purchased with an initial investment of 1 hour and 40 minutes during construction. The return ratio is approximately 8 to 1. Every hour invested in careful plumb checking returns roughly 8 hours of avoided future work. This analysis excludes catastrophic failures. Structures that collapse under extreme snow loads require complete rebuilding, not simple maintenance. If even one of Crew A's poorly aligned posts contributes to a catastrophic failure, a shed roof collapse, for example, the cost escalates dramatically. Rebuilding a small shed requires 20 to 40 hours of labor plus materials. The loss of stored goods, hay, grain, tools adds further economic impact that does not appear in simple time calculations. Extend this analysis to frontier districts with hundreds of homesteads and ranches, each setting similar numbers of posts per season. The aggregate difference between careful and casual plumb practice amounts to thousands of hours of labor across a region over a decade. During severe winters like 1880 to 81 or 1886 to 87, that difference determined which operations survived intact and which faced compounded crises of failed structures, lost supplies, and inadequate shelter. The ledger math was clear even if few frontier builders calculated it explicitly. Time invested in doing work right, defined quantitatively as within 2 degrees of plumb on each face, returned multiples in reduced future labor and risk. The pocket plumb, or any similar method that made consistent plumb checking fast and practical, shifted the cost-benefit ratio decisively toward careful work. Contemporary extension bulletins from the early 20th century made these calculations explicit. A 1915 Montana State College publication on farm building economy stated, 1 extra hour of care during construction typically saves 5 to 10 hours of maintenance over a building's useful life. This ratio holds especially true for work requiring precision, such as post alignment, which determines load distribution and long-term structural stability. The principle extended beyond individual homesteads. Communities where builders adopted careful plumb practice, whether through formal tools or disciplined technique, showed measurably better building performance over time. Fewer emergency repairs during winter, lower rates of catastrophic failure during extreme weather events, and longer average service life for agricultural structures all contributed to greater economic resilience. These outcomes were not dramatic. No single carefully set post prevented a disaster or saved a homestead. But across seasons and structures, the accumulated advantage of consistent vertical work created a margin, a buffer against the next hard winter, the next unexpected load, the next confluence of adverse conditions that would test every structure in a district. In account book terms, a scrap of leather and a cast-off weight bought back days of labor and reduced the risk in the worst years. A small brass pocket level appeared in the Montgomery Ward catalog for spring 1902, priced at 35 cents. The item description read, "Pocket spirit level, suitable for fence posts, small framing, and general carpentry. 3-inch length, 2 vials for level and plumb reading. Durable brass body." The illustration showed a compact tool small enough to fit in a work coat pocket, with bubble vials visible in simple frames. The appearance of pocket levels in mass-market catalogs marked a transition. Tools that had previously required specialized manufacturing and distribution through professional supply houses became accessible to general consumers. Prices dropped as production scaled up, and standardized designs replaced custom or limited-run models. Earlier catalogs show the evolution. An 1885 Hardware Jobbers catalog listed spirit levels in sizes from 6 inches to 48 inches, priced from $1.50 to $12 depending on length, materials, and quality. These were professional tools sold through building supply dealers to carpenters and contractors. The catalog made no mention of pocket-sized levels or specialized post-setting tools. By the mid-1890s, smaller levels began appearing. An 1896 Sears Roebuck catalog offered a handy level at 75 cents, described as compact and convenient for the farmer or homeowner. The tool measured 6 inches long and included a single vial for checking level surfaces. A notation indicated it could be used vertically for plumb work with care. The 1902 Montgomery Ward pocket level represented further refinement. Dedicated plumb and level vials in a purpose-built compact housing, explicitly marketed for field applications, including fence posts. Similar tools appeared in other catalogs over the next decade. By 1910, several manufacturers offered post levels, small bubble levels integrated into clips or caps that attached directly to the post being set. These manufactured tools embedded the same principle that a leather strap plumb used: provide a portable, reliable reference that the worker can apply quickly without stopping work or requiring an assistant. The difference lay in the display mechanism. A strap plumb used beads aligned against a vertical edge. A pocket level used a bubble centered in a vial. Both relied on gravity, either the weight pulling the cord to vertical or the bubble rising to the highest point in the curved vial. Agricultural extension publications reflected this tool evolution. A 1908 Iowa State College Bulletin on Farm Building included detailed recommendations on post setting, with illustrations showing a worker using a small level held against a post face. The text specified, "Check each post for plumb on 2 adjacent sides before tamping more than 1/3 of the backfill. A pocket level costing less than $1 will serve this purpose adequately." By the 1920s, post-setting tools became even more specialized. Catalogs listed post caps with built-in levels, metal or wooden caps that fit over the top of a post, and included bubble vials oriented to show plumb in multiple directions simultaneously. Prices remained low, typically under $1, making the tools accessible, even to small-scale operators. The continuity across this tool evolution is clear. Whether using a plumb line, a leather strap with beads, a pocket level, or a post cap, the underlying task was identical. Compare the post's orientation to a reliable vertical reference provided by gravity. The progression represented improvements in convenience, durability, and ease of reading, but not changes in fundamental principle. This technological continuity suggests that the frontier use of improvised strap plumbs, while not extensively documented in formal records, fit within a logical progression. Builders who understood the principle of plumb work but lacked access to manufactured levels would naturally develop field-expedient alternatives using available materials. As manufactured tools became cheaper and more widely distributed, these improvised methods would fade from active use, leaving little trace in the historical record except where their effects remained visible in the performance of structures they had helped build. The diffusion pattern followed typical agricultural technology adoption curves. Early adopters, professional builders, progressive farmers, and those who had experienced structural failures invested in new tools first. Word-of-mouth recommendations and demonstration effects spread adoption through social networks. Extension education and agricultural bulletins formalized best practices and tool recommendations. By the 1920s and 30s, careful post-plumb checking with appropriate tools became standard practice, codified in building guides and taught in vocational agriculture programs. European practices showed parallel development. British and German agricultural literature from the same period emphasized vertical alignment in fence and shed construction, with specific recommendations for using plumb tools at each post. The principle was universal. The specific implementations varied by regional material availability and building traditions. By the time pocket levels were cheap and common, the idea they embodied had already been at work wherever a cord and weight could hang. A worn leather strap hangs on a nail inside a preserved homestead cabin near De Smet, South Dakota. The strap measures roughly 20 inches long, darkened with age and use. 2 glass beads remain in place, one fixed near the top, one held by a tight knot farther down. At the bottom, a flattened lead weight shows the wear of repeated contact with wood and soil. The cabin itself stands straight. Porch posts remain plumb after more than a century. Interior roof beams show no sag. The structure has required maintenance over the decades: roof patching, chinking repair, foundation work. But the basic frame remains sound, a testament to careful original construction. This cabin is one of many frontier structures that survived not through exceptional materials or heroic construction efforts, but through methodical application of basic principles. Gravity provided a universal reference. Simple tools made that reference accessible and repeatable. Consistent attention to vertical alignment created structures that distributed loads properly and resisted progressive failure under stress. The quantitative outcomes of this approach, extrapolated from documented cases and engineering analysis, tell a clear story. Hours saved during construction through efficient plumb checking methods. Reduced maintenance requirements over decades of use. Lower failure rates during extreme weather events. Longer service life before major rebuilding became necessary. Fewer emergency repairs during seasons when labor and materials were scarcest. These advantages multiplied across frontier districts. A homestead that set 50 posts per season using methods that saved 3 minutes per post recovered 2.5 hours of productive time. A ranching operation setting 200 posts reclaimed 10 hours. Extended over 5 or 10 years of active building and expansion, the accumulated savings reached weeks of labor. time that could be invested in other essential tasks or simply reserved as margin against unexpected demands. The structural benefits extended beyond time savings. Fences that stood straight were more effective at containing livestock and marking boundaries. Corrals with plumb corners and gates functioned reliably under pressure. Sheds and porches that maintained their geometry required less frequent repair and provided better protection for stored goods and occupants. During severe winters, these differences became matters of survival. The 1880 to 81 winter tested every structure on the northern plains. Those built with care and attention to load paths generally stood. Those built hastily with minimal checking often failed. The difference was not random luck or exceptional materials, but the accumulated effect of dozens of small decisions made during construction months or years earlier. Contemporary observers sometimes attributed survival to individual toughness or divine providence. Later analysis reveals more prosaic factors: adequate post depth, consistent vertical alignment, proper bracing, and maintenance of load-bearing capacity through all phases of structural loading. These technical factors determined outcomes more reliably than any human virtue. The broader lesson extends beyond post-setting methods to frontier building practice generally. Engineering discipline, even when applied with improvised tools and limited formal training, consistently outperformed casual practice under extreme conditions. The frontier did not reward bravado or haste. It rewarded careful work, systematic checking, and appropriate conservatism in structural design. The pocket plumb, whether recognized by that name or not, represents a category of small innovations that characterized successful frontier adaptation. These were not revolutionary inventions or dramatic breakthroughs. They were practical adaptations that solved specific problems with available materials. Their value lay not in novelty, but in effectiveness. They worked, they spread through informal networks, and they improved outcomes for those who adopted them. Historical documentation of such tools remains sparse because they were considered mundane. Patent records focused on novel mechanisms worthy of legal protection. Trade catalogs listed manufactured goods sold through commercial channels. Building manuals described formal carpentry techniques taught in apprenticeship programs. Field expedient methods used by homesteaders, ranch hands, and itinerant builders left little written trace, visible primarily in the performance of structures they helped create. Modern heritage preservation efforts occasionally uncover physical evidence: a leather strap with beads in a preserved homestead, an improvised plumb bob fashioned from a bullet or fishing weight found in a tool cache. These artifacts, when they appear, suggest patterns of practice that were once common but never formally recorded. The final accounting is simple. In a landscape where one winter could erase a careless season's work, the frontier advantage did not belong to the strongest crew, but to the one that turned gravity into a reference and wrote its own margin of safety into every post. If you value fact-grounded frontier history and detailed looks at how people actually built and survived in the West, consider supporting the channel.